So we're going to start off looking at our conservation of mechanical energy concepts with a graphical perspective. So let's say you have a roller coaster. Of course, a roller coaster will go slowly over the tops of these curves here and speed up at the bottom. So from an energy perspective, what's going on there is if I graph EG, so that's the gravitational potential energy. So remember, the gravitational potential energy is just mgh or mgy. M is the mass of your coaster. G, so that's going to stay the same the whole time. G is just 9.8 because this is on the surface of the Earth. But H is going to change. And H, of course, is the height above the ground. So as H is high, you'll have high gravitational potential energy here. And as H gets lower, your gravitational potential will get lower too. So your graph of the gravitational potential energy should actually just follow the shape of the roller coaster itself. So that's EG. But at the same time, I have this mechanical energy which is going to be conserved. And because of that, that means that my kinetic energy will speed up every time I get to one of these lower spots in the roller coaster and slow down at the crest. So if I graph my kinetic energy, so EK, so it's kinetic, which is a half mv squared. The mass stays the same the whole time, but the velocity definitely changes. We'll be going pretty slowly over that crest. When we get to point B here, it's going to speed up and be going really fast at point B. Point C, though, I'll slow down again, and then I'll speed up again as it goes down that hill there. So that would be my EK here. So that's EK, and this here is EG. Now, the mechanical energy is, of course, EK plus EG. It's the kinetic plus the gravitational. And what you should notice is that if I add together this pink line and the blue line at any moment in time, it should add up to the same value. So this is the mechanical energy here, and it will be constant throughout the whole trip down the coaster. So if your gravitational potential is high, then that means your kinetic is low. But as your gravitational potential drops off, your kinetic energy gets higher, you speed up, and so you keep the same overall mechanical energy. All right, here's another example of a concept with mechanical energy. So let's say you have these two roller coasters. So one of them, they both start at the same height and they both end at the same height. But one of them goes sort of like at that high height for a while and then has a slope at the end. The other one has a really steep slope early on and then goes flat for a while. My first question is just which one would have a faster traveling car at the end? So when your car gets to the end, will you be going faster if you took path A or path B? Well, we can actually use our conservation of energy equation here, which is that mgy1 plus a half mv1 squared equals mgy2 plus a half mv2 squared. So first thing you want to notice is actually that the mass is in every single term here, so the mass will cancel out, right? You could divide every term by mass and it's just going to be gone then. So this doesn't depend on mass at all. So notice doesn't depend on mass. So this doesn't matter if you have a really heavy roller coaster car or a really light one. It's not going to make any difference in the final speed. Both of them will be going the same speed at the end. But it does matter sort of what height you start at. So what's y1? And both of these paths have the same y1. It matters what their initial velocity is. And both of them start at rest. So that's the same v1. It matters what your final height is, which is y2, and they're the same for both path A and path B, which tells us that they must be traveling the same speed. Everything else in this equation is the same, right? Of course, g is the same for both of them. They're both on the same planet. So they must have the same speed at the end. So whether you take this path or that path or a path, you could do another one like this that has like a hill and a loop-de-loop in there, that doesn't actually matter. If they start at the same height, end at the same height, started at the same speed initially, they'll have the same final speed. All right, I'll just erase my extra path in here. Okay, what about their delta t though? Like how long it takes them to get through that path. For delta t, it matters how fast I'm going during the journey, right? So they have the same v2 for sure, but they don't have the same speed during the journey. So path A is going to be slow up here, right? Really slow, and then it'll finally get going fast just at the end. Whereas path B is going to get going fast pretty early and then stay fast for most of the time. And so path B, they'll both reach that same fast speed at the end, but if you take path B, you'll be going that fast speed much earlier, which means you're going to have a shorter delta t. So path B will reach the end sooner, shorter delta t, but both of them have the same speed when they get to the end. All right, what if path B starts a little bit higher, path A is a little bit lower down originally? Well, in this case, when I write down my conservation of energy equation, half mv1 squared plus mg y1 is half mv2 squared plus mg y2. In this case, they do have the same y2, and they both start from rest, so they have the same v1, but the y1 for path B is higher. So path B has a higher initial starting point, which means that path B will be going faster at the end. So it'll have a higher or faster V2 as well. So if you start from a higher initial height, you both end at the same height, then the path that started at the higher initial height will have a faster speed when it gets to the end. All right, what about these three scenarios? So first we have a ball being thrown up in the air from a height of 3 meters off the ground with an initial velocity of 5 meters per second straight up. So here's the ball. It's being thrown just straight up with a V1 of 5 meters per second and a Y1 of 3 meters above the ground. So that's A, situation A. Situation B looks like this. You have a ball being thrown straight down, V1 of 5 meters per second, and a Y1 of 3 meters off the ground. Or option C, so you have a ball being thrown at an angle here, 30 degrees. The V1 is 5 meters per second, and the Y1 is 3 meters. And all of these are going to hit the ground. So that means for all of them, the Y2 is going to be 0. So Y2 will be 0, Y2 will be 0. But they'll all clearly have different paths, different trajectories. So this first ball is going to go way up, right, and then come down and hit the ground. So that's its kind of trajectory here. It'll hit the ground. This ball is just going to go straight down and hit the ground. And this ball is going to go through a parabola and hit the ground over here. So they all have different paths. What we want to know is which one is moving the fastest or has the highest V2 at the moment when it hits the ground. So we can use our energy conservation equation here too. So half m v1 squared plus mg y1 will equal a half mv2 squared plus mg y2. So they all hit the ground, which means this term is 0, right? Because y2 is 0. And then if I look on this side here, all three of these balls here start with 5 meters per second for their V1. So they all have the same V1. They also all start from the same height. So they all start from 3 meters above the ground, which means they all have the same V2. So they all have to hit the ground with the exact same speed. Now, some of them will be in the air for a longer time, right? This one's going to have a lot of hang time in the air because it follows this big parabola up here. This one's not going to have much hang time at all, like it's going to go just straight down, so it'll hit the ground in less time. But when these balls hit the ground, the speed they're moving just before they hit the ground is the same in all three of these pictures. So their final velocity, V2, will be the same regardless of what direction they're thrown in if they start at the same height and they have the same initial velocity.